Hello. We are going to learn about, and you sure the numbers are like going 1, 2, 3? That's
yeah, 5, 6, 7.
Okay, great. And this is Hazel, who's actually doing the what do you call it, movie
Recording?
making. She's the videographer. We are going to learn today about rotational kinetic energy. That's it. Rotational kinetic energy. Here, is there anyone in this class who's ever either, if you're a boy, you've played baseball, or if you're a girl, you've played softball? Okay, come on up here, Diego. And you'll stand over here. Sure, it doesn't matter. Because you've played baseball, you've had the opportunity to throw a bat to somebody, right? A bat who's a friend. And you don't want them to be hurt when you throw them the bat. You guys see that? And so I want you to throw me the bat, but throw it in such a way that it does not hurt me. Let me ask you, how are you going to throw that to me? No, not like that. Not like that at all. Someone who's actually done this. Well, how should he throw it so that it doesn't hurt me? Justin, look at Justin. Explain. How do I do it?
Toss it upwards.
Oh yeah.
Yeah, right. Here, throw me the bat. Throw me the hammer. Yeah, you see that? Here, I'll throw it to you. You see that? It does not hurt us. It doesn't hurt us because we're making sure that it does not have what type of kinetic energy? Yeah, rotational. Tell me, should I try to spin this hammer as fast as I can as I toss it to him? No. This big head, that would be really bad. It would really hurt him. So as long as we make sure that this hammer doesn't rotate, it's very easy for us to catch. All right, give Diego a hand. Yay. So let me show you, you see that trash can there? I'm going to throw this hammer at pretty much the same speed as what Diego and I were doing, but now I'm going to try to spin this hammer really, really fast. And I want you to see the sort of damage a spinning hammer can do when it has lots of rotational kinetic energy. Well, I missed.
Scandalous.
You see, it kind of tore this a little. I don't know. But you guys get the idea. That you certainly don't want this hammer hitting you while it's spinning. So let's talk about rotational kinetic energy. In linear land, we know that kinetic energy, which I'm now going to call translational kinetic energy, we know that in linear land, translational kinetic energy is 1/2 mv squared. How about in rotation land? What do you suppose rotational kinetic energy is going to be equal to? Go ahead, Win. Oh, I'm sorry. Go ahead, Diego. Thank you. 1/2 I omega squared. Don't say W, it's I. Like Cameron Adams last period said W, and I laughed at her. Yeah, 1/2 I omega squared. It's the same variables, only the rotational versions of those variables. And I hope you realize you don't really need to memorize any of the rotational formulas. They're all just like their linear counterparts. All right, so let's go ahead and do a problem. Here comes example number 1. A 1.2 kilogram ball on a 0.80 meter string rotates around at 0.50 revolutions per second. Find the rotational kinetic energy. I'd like everyone to please plug in now. I'll give you a minute. So I'll have a minute where that's just, we're not doing anything.
Okay.
I get a picture come off. Does everyone know ball on a string? What's the formula for the moment of inertia of a ball on a string? That's the disk.
Mass times velocity. No. Mass times distance.
Good. And what do you do with the distance?
Square it?
Yeah, mr squared. You guys okay with that? Mr squared. If it's a point mass, then the rotational inertia is mr squared. And then here's the last thing. My omega is 0.50 revolutions per second. But I gotta tell you something. Whenever you're dealing with newtons or joules, you have to be in radians. I wanna make it really clear, this equation only works in radians. Because we need to have those relationships between theta, omega, and alpha being derivatives of each other, and that only works if you're in radians. So I can't have 0.5 revolutions per second. I'm going to have to convert to radians. So this is going to be 2 pi radians over 1 revolution, and then I square it, and now I'm going to get my rotational kinetic energy. It's really, really important that you know that this formula only works in radians, and textbooks and exams will try to fake you out by giving you omega in some other unit, but it has to be radians. So I'm getting like 3.8. You guys okay with that? Okay, then I'm going to continue. Here comes example 2. Just 1 second, I need my notes. I forgot the numbers I used. A 3-kilogram cylinder of radius 0.50 meters is rolling at 6 meters per second. Find its total kinetic energy. Okay, before we do this problem, I need to explain something conceptually. There are 2 types of kinetic energy. There's translational kinetic energy and rotational kinetic energy. And these 2 kinetic energies are completely independent of each other. For example, if I threw this hammer from my right hand to my left hand, but I threw it in such a way that it was spinning in the air, then the total kinetic energy of the system would be the sum of the translational kinetic energy, which is 1/2 mv squared that I get from my hammer just flying through the air, and the rotational kinetic energy, which is how much kinetic energy the hammer would have if it was just at rest and it was rotating however it was rotating as it flew through the air. So when you add this kinetic energy, where it's just stationary but rotating, to this kinetic energy, you get the total kinetic energy of the system, which is the kinetic energy of this hammer as it's flying through the air. Well, the same thing happens when an object is rolling along the ground. Imagine I have a cylinder that looks like this in contact with the ground, and the cylinder is rolling. Okay. Well, if the cylinder is rolling at 6 meters per second, that means that the velocity of the center of the cylinder is 6 meters per second. In this case, I'll just call it V. That means if this wheel were attached to a car and there were 3 more wheels, and this wheel is rolling at 6 meters per second, that's the speed of the axle, which means that's the speed the car would have, 6 meters per second. But here's the thing. when something rolls without slipping, the wheel is momentarily at rest here. I know that the wheel isn't moving relative to the ground because I'd hear squealing like something skidding out. And so whether it's a wheel or any other cylinder or a ball or whatever, if something's rolling without slipping, the velocity at the point of contact with the ground is always going to be 0 because it's rolling without slipping. And then finally, I've got something where this velocity is v, this velocity is 0. What's the velocity of this point going to be? Well, this is like it's momentarily, the cylinder is momentarily rotating about this point. And so if that's v, this velocity would be 2v. And those are the velocities on your wheel as it rotates. At rest, where it's in contact with the ground, v, which is the velocity of the axle, and then 2v, which is the velocity of the top part of the wheel. Well, this rolling, I can actually separate into the two types of kinetic energy, translational and rotational, just like I did with the hammer. I can say that this is the sum of a translational component, where this velocity is v, this velocity is v, and this velocity is v. Like the wheel was just sliding on a frictionless floor at a velocity of v, plus the rotational component, such that this velocity would be, because it's rotating this way, okay, this velocity b would be to the backwards, this velocity would be 0, and then this velocity would be v in that direction. This is the translational component of kinetic energy, and this is the rotational portion. Not component really, because they're not vectors. This is the rotational component of kinetic energy. You see? And do you see how the velocities work out? Why is the velocity in contact with the ground 0? Because it's the sum of this velocity and that velocity, two equal and opposite velocities. So I get 0. Why is this v? Because the translational part of the kinetic energy requires the axle to move to the right at v, but the rotational part, the axle's at rest. And then finally, this guy's 2v because I got v plus v, and that gets me 2v. So I hope you see that when someone asks you for the total kinetic energy of something that's rolling, you're going to have to find the translational kinetic energy, the rotational kinetic energy, and then add them up. And that's what I'm going to do right now. Here we go. For the translational kinetic energy, I'm just going to use 1/2 mv squared, the formula that's right here. So I got 1/2 times 3 kilograms times 6 meters per second squared. That's 36, what is that? 1/2, 36, 18 times 3 is 54, so I got 54 joules. That's the translational kinetic energy. The rotational kinetic energy is 1/2 I omega. So I got 1/2 times. I hope you remember that the formula for the moment of inertia of a disk is 1/2 mv squared. So I got, 1/2 mr squared. And then for my omega, because this rotational is just circular motion, I get to use theta equals s over r, and thus omega equals v over r, as long as I'm in radians. I get to use that formula, so I'm going to put v over r for omega. Oh, that's squared. 1/2 I omega squared. My bad. And then I'm going to put v over r in, squared. And what do you notice happens to the radius of the cylinder? What happens to the radius?
Cancels out.
Yeah, it cancels out. I told you the radius of the cylinder is 0.5 meters, but frankly, did it matter what the radius was? No, because the radii cancel. So I end up with 1/2 of 1/2 mv squared, which means I'm going to get half of that 54 joules, or 27 joules. So now I get an expression for the total kinetic energy of the system. the total kinetic energy, which is going to be 54 joules plus 27 joules, or 81 joules. Yay. Any question or problem on this before I have you guys do one just like it? Okay, then here we go. Okay. Example number 3. Get the total kinetic energy of a 3 kilogram hoop going 6 meters per second. Please do this now. You're going to do the same process, but now it's a hoop that's rolling. When I say going 6 meters per second, I really should say rolling at 6 meters per second. All righty, good luck. I'll give you like a couple minutes. And I want to remind you, what's the moment of inertia for a hoop?
1/2.
Not 1/2. It's just mr squared, because a hoop, all the hoop is a point mass, but it's a collection of point masses, but they're all as far from the point of rotation as possible. So it's just a bunch of mr squared. So the total moment of inertia is mr squared. Are you guys getting the same answer for the translational kinetic energy? Are you guys getting 54 joules for the rotational kinetic energy also? Great. So in this case, the total kinetic energy is equal to 54 joules plus 54 joules, which is 108 joules. Can I ask you a question? Why is the rotational kinetic energy so much bigger here than there? I mean, that's 54, that's 27. Why? Yes, when? Yes, tell me specifically what's bigger for the hoop?
The inertia.
Yeah, the inertia, the moment of inertia, right? It's mr squared versus 1/2 mr squared. So because the hoop has a greater moment of inertia, it's going to have more rotational kinetic energy. There's another way to think of this. What fraction of the total kinetic energy is rotational? Well, with a hoop, when I've got a hoop that's rolling, you tell me what fraction of the total kinetic energy is going to be rotational. What's that? Well, okay, but so of the total 108, what fraction is rotational? Yeah, half. You guys okay here? Okay, 1/2 of the total kinetic energy is rotational. That's what I've got when a hoop, any hoop that's rolling, half of its kinetic energy is rotational and half of it is going to be translational. Look at the cylinder. What fraction of the cylinder's total kinetic energy? Yes? Yeah, you guys okay with that? Here, if I've got a cylinder that's rolling, only a third of its total kinetic energy is rotational. Only 1/3 of the total kinetic energy is rotational. Not a half. And the reason, you'll always get twice as much translational as rotational when you've got a cylinder that's rolling. Why is that? Because the moment of inertia is so little. Any question or problem on this? Okay, then it is time for us to do example number 3.
4.
Example number 4. Thanks. Here it is. A basketball. And by the way, the basketball is a hollow sphere, not a solid sphere. The moment of inertia of a solid sphere is 2/5 mr squared. But the moment of inertia of a basketball, a hollow sphere, is going to be 2/3 mr squared, because all of its mass is concentrated really far from the center of rotation. A basketball rolls down a ramp, has final speed of 5 meters per second. How high was the ramp? Well, let's go ahead and make a drawing. Here's my ramp. Here's my basketball. It starts from some initial height h. And then when it reaches the bottom, it's going to have a speed of 5 meters per second. Is there friction? We're assuming this is rolling. It says it rolls down a ramp. We'll assume it's rolling without friction. What I mean is it's rolling without slipping, is what I'm saying. So tell me, is there friction between the ball and the ramp? Must there be friction for something to roll without slipping? Absolutely. Because if this were totally frictionless, what would the ball do? Yeah, just slide down without rotating, right? It would just slide down, So there must be friction. So the next question is the friction doing any work?
Yeah.
Well, let's see. Here's the point of contact that's where the friction is happening, okay? In order for friction to do work, the friction has to do a force over a distance. Is this point moving relative to the ramp? Yeah, no. The point's not moving relative to the ramp. So although there's friction to make it roll, that friction's not doing any work. Not like if I slide a box along the floor where friction is now doing work because friction's acting that way and the box is moving that way, and so friction's going to do negative work on the box and slow it down. But that's not what's happening here, because at this moment in time that point's not moving. And then, a moment later, it will be replaced with another point that's in contact with the ramp that isn't moving relative to the ramp while the friction is acting. And so you get this weird situation where there's friction that causes it to roll, but that friction does no work. And so because there's no work being done by non-conservative forces, what thing is going to be conserved? What's that? Thank you very much. Mechanical energy, not momentum. If this were a collision, we'd say, oh yeah, momentum's conserved. But there's no collision happening here. But mechanical energy is conserved. Mechanical energy is conserved because there's no non-conservative work being done. There's friction, but it doesn't do any work. So here we go. Initial mechanical energy equals final mechanical energy. What kind of mechanical energy does this have initially?
Potential.
Yeah, gravitational potential, MGH. So we got MGH. What kind of energy does it have when it reaches the end of the ramp?
Kinetic energy.
Say again?
Kinetic energy.
Kinetic energy. What kinds of kinetic energy?
Rotational.
Yeah, it's got rotational because it is rolling. Does it have translational as well? Sure, because it's in motion, right? It's not, stationary while it's rotating. It's in motion. So I hope you see that I'm going to have translational kinetic energy plus rotational kinetic energy. Let's go ahead and plug in. I got mgh equals my translational, which is 1/2 mv squared, plus my rotational, which is going to be 1/2 I omega squared. You guys okay with that? And so I've got mgh equals 1/2 mv squared plus 1/2 times the I of the basketball, which is 2/3 mr squared, times omega, which we can always substitute V over R for omega because it's something rolling. The rotational kinetic energy is just something that's stationary, that's spinning in a circle like a turntable. What's one thing that you notice cancels? Yeah, mass cancels. So did you notice why I never got around to telling you what the mass of the basketball was? Because it cancels. So hoop, hoop, oops, well, no, I'm one. Hoop, hoop, hoop. What else cancels?
Radius.
Yeah, the radius, boop, boop. And so it doesn't matter how big the basketball is or how small. Any basketball I put at the top of the ramp is going to end up with the same velocity at the end because the radii cancel and the mass cancel. All basketballs roll down ramps at the same rate. And so now I've got GH equals 1/2 of V squared plus 1/3 of V squared. And now I can plug in for V. 9.8 times H equals 1/2 times 5 squared plus 1/3 times 5 squared. And so I get H equaling approximately 2.1 meters. And it doesn't even matter what the angle of the ramp was. Yes?
What happened to the two? No, we know the masses and the radius.
Yeah, they all canceled. The 2's cancel as well.
Yeah.
Yeah. What time is this crazy class over? 53?
Crazy class.
6 minutes.
53. Cool. So here's the last thing I want to talk about. This problem, let me think, what should I have? This problem makes a really important point. It says that all basketballs roll down ramps at the same rate, regardless of mass and regardless of radius. And it's true for all spheres as well. All solid spheres roll down ramps at the same rate. Because again, if instead of 2/3, if I had 2/5, because it's a solid sphere, I'd still have all the m's canceling and all the r's canceling. And the speed ends up being independent of m or r. So that's actually an interesting fact. All spheres, all solids, where am I going to write this? Maybe I'll write it over here. All solid spheres roll down ramps at the same rate. And it's not just true for solid sphere, it's true for anything. All hoops roll down ramps at the same rate. Or all cylinders roll down ramps at the same rate. I'm going to try to demonstrate that for you now. Let me see. Well, this isn't really that's not really a cylinder. Maybe I can get a couple of spheres. Yeah, let's try a couple of spheres. Oh, this isn't a perfect sphere either. Just 1 second. Here we go. We're going to discover whether science is true or a lie. I have 2 spheres here. Maybe I can get a bigger sphere. Sorry, Hazel, I keep changing my position.
It's okay.
Here's an even bigger sphere, although it's got some stuff attached to it. Let's try it. So first of all, let's try these 2 spheres. One sphere is significantly bigger than the other. One sphere, yes, thank you. One sphere is made actually of a different material. This sphere doesn't look like it's steel, or at least it's got a different color to it. Maybe it's a different type of steel. Okay, but you would think, well, one's heavier and the heavier one has a bigger radius. Shouldn't it go down the ramp at a different speed? And the answer is no. Supposedly, these 2 spheres should roll down the ramp at the same rate. Here we go. What? Did you notice the big sphere like got a head start? Like I like removed the ruler and the big sphere started rolling and the little sphere didn't. What the heck's going on with this? You know what we can conclude?
Science is a lie.
Science is a lie, absolutely. Here, let's try this again. Okay, stop that. Stupid sphere. Okay, here we go. 1, 2, okay, the big sphere won the first race.
Yes, sir.
Oh my gosh, now the little sphere won.
Maybe it's the side on the.
It must be. I changed the sides, and it just seems like the little sphere. I mean, whoever's on this board gets a head start. Whoever's on this board like gets stuck. That's weird. Why is that? Or is it just completely random? Here, let's see if it's completely random. Stupid things. Okay, here we go. Here we go. Well, that time the little sphere got a really big head start. Yeah. I don't know. It's like I try to do this demo and it just never works. Like science just continues being a lie. Even though, honestly, supposedly I should get my bowling ball and this sphere and they should go down ramps at the same rate. Here, let's try a metal sphere and a wooden sphere. Well, that was weird. You see, I mean, I didn't do a very good job of removing the ruler. Like the wooden sphere like went that way. So here, let's see if I can do it right. No? I don't know.
If you're on like that side of the room, it'd be like it'd come faster or something.
I don't know. Yeah, or maybe there's just slight. But these 2 boards seem pretty similar. Oh well. Anyway, supposedly that's true, even though I totally haven't demonstrated it at all whatsoever. Alrighty. Well, tonight's homework, 2 of the problems are on the other side of the Xerox I gave you, so make sure you do those problems 3 and 4, and we're done. Bye-bye.